was this one, that atomic radii generally increase as we go down a group. Let's look at that. So here I've copied our illustration of lithium to neon, but I've added sodium, which of course is in the same group as lithium. What do you notice as a difference between lithium and sodium? You know this. The highest main occupied energy level is the same as the period in which the element occurs. Because sodium is in the third period, we've added a third main energy level. Well, what does this mean in terms of atomic radius? Remember how we said that as we added electrons on the outermost occupied main energy level, the force from the nucleus was able to pull that outermost energy level in more tightly? Well, that's true, assuming that we haven't put anything in between the nucleus and the outermost main energy level. As we add outermost main energy levels with sodium and on with with sodium and then on to potassium, we're actually adding a main energy level every single time. What that means is that there are a whole lot of electrons in between the nucleus and the outermost main energy level, and the nucleus can't pull it in nearly as tightly. If we look at potassium, we see that there's a whole lot of shielding between that outermost main energy level and the nucleus. As a matter of fact, this is actually called electron shielding. And what it means is that in larger atoms, the more main energy levels that we have between the nucleus and the outermost occupied main energy level, the more those inner shell electrons shield the outer shell electrons from the effects of the nucleus, meaning that they tend to get bigger and fluffier. Now, here's the other trend that we know about. Reactivity, especially in the metals, tends to increase as we go down a group. So if you look at group 1, lithium is more reactive than hydrogen in its solid form. Sodium is more reactive than lithium. Potassium is more reactive than sodium. Rubidium is more reactive than potassium. You get the picture here. You should watch the video too. Well, why is that? In the metals, what does reactivity depend on? In the metals, reactivity depends on the ability to give up that outer shell electron and become an ion and to react with something else. Well, the farther out from the nucleus, the more shielded that outer electron is, the easier it is to pull it away from the atom. So, as we add main energy levels between the nucleus and the outermost main energy level that's got electrons on it, the more shielded those valence electrons are, and the easier they are to pull away. So hence, in the metals, as we go down a group, things tend to get more and more and more reactive. Notice that I said in the metals. Let's talk about the non-metals for a second, and specifically, let's talk about the halogens. We're going to forget hydrogens over here. So the halogens are very reactive, but their reactivity is a little different than that we see in the metals. Halogens' reactivity depends on being able to add an electron to this outermost shell and become an ion. So their reactivity depends on being able to attract an electron. Would electron shielding make that easier or more difficult? Well, in order to attract an electron, you have to have that pull exerted by the nucleus pulling on an electron to add it to your outermost shell. It kind of seems like electron shielding would make that harder, doesn't it? In fact, what we see in the halogens is a reverse pattern of reactivity, where fluorine is the most reactive halogen, chlorine slightly less reactive, bromine less reactive than that, and you can actually have pure iodine sitting in a room and it won't necessarily react with anything, though it'll happily form compounds. So the patterns of reactivity that we see in metals and nonmetals are actually reversed. due to the same underlying effect, electron shielding. So if I took strontium, magnesium, and barium, these are all group 2 elements, and asked you to arrange them in order of increasing radius, how would you do that? So that's smallest radius to largest radius. Would you say magnesium, strontium, barium? Of course you would, because that's how we find them going down the periodic table: magnesium, strontium, and barium. Now, if I asked you to arrange them in order of increasing reactivity, how would you do that? Oh wait, you say it would be the same thing? Smallest reactivity to largest reactivity? Yeah, you're right, because reactivity increases as we go down a group due to electron shielding. Radius increases as we go down a group due to electron shielding. Okay, so the big takeaway: atomic radius decreases as we go across a group, that is from group 1 to group 18, because of the increasing attraction of the nucleus to outer shell electrons, with no additional layers of sort of insulation between them. Atomic radius increases as we go down a group because while we're not adding any more electrons in the outer shell, remember, groups share an outer shell configuration, we are adding shells between the pole of the nucleus and those outer shell electrons. Reactivity in the metals follows the exact same pattern as atomic radius. Metallic atoms with smaller radii tend to be less reactive because the nucleus has a better grip on those outer electrons. As atomic radius increases, reactivity tends to decrease tends to increase as well, because the nucleus can't get as strong a grip on those outer electrons due to electron shielding. In the halogens, the reactivity pattern is reversed, because halogens' reactivity is dependent on attracting an electron. So the smaller the radius of the atom, the stronger a pull the nucleus can exert on the outer shell. Okay, look over the practice, keep moving. Oh, and watch the video about the alkali earth metals. Lots of fun, alkali metals.